Hello, my name is Paveshwan Analaki Krishnan from SACC. Today, in instrumental analysis, I'm going to talk about optimization instrumental condition for the analysis of mercury, arsenic, antimony, and selenium by atomic absorption spectroscopy. Okay, the chemical vapor generation atomic absorption spectroscopy techniques is extremely popular. For now, we can focus on the hydride generation continuous flow system for the arsenic, antimony, selenium, and the cool vapor is for the mercury. So the optimizing of the instrument the optimizing instrument of the parameter as well as the hydride generation reaction will produce sensitivity and reliability of the result obtained. So the advantage of the optimizing the condition increase the production of the hydrides or the vapor species form. So let's talk about the optimizing of the parameter. In order to optimize the parameter to be increased, the production of the hydride and the vapor must be the higher, and by improving the recoveries. So this will actually reduce the chemical interference of the other species. So let's talk about the parameter. There are many types of the parameter. First is the reagent, sample, or the argon flow rate. Next is the acetylene air ratio, concentration of the reagent, and the read delay time. Okay, now the hydride generation technique involves three distinct processes. The first one is hydrogeneration and release of the element of interest from the sample solution, whereby the sample solution converted to the hydride transferred to the gaseous phase with the aid of the reducing agent. Next, this is the optional, whereby the hydride collection. Then finally is the main thing, which is the atomization, whereby the transport of the released hydride into the atomizer by the flow of inert purge gas. Okay, next is the factors that influence the yield of the hydride and the sensitivity of the technique. First, a factor which is the concentration of the acid, concentration of the type of reducing agent. Next is the flow rate. The flow rate, first is the flow rate of the carrier gas, flow rate of the reducing agent, flow rate of the acid, and then the read delay time of the sample. Next, we focus on the principle of the cold vapor AAS, whereby first the SnCl2, which is the reducing agent, is used to convert the ionic metal of the mercury to mercury gas, which produce high analytical absorbance signal. Mercury, which is having a very high vapor pressure, is liberated and entrained into inert gas of argon after passing to the liquid gas separator. Next, the mercury vapor is transferred into a optical path of the atomic absorption spectrometer, where the mercury absorbs the light specific wavelength at the room temperature. So the sensitivity and the precision can be maximized by optimizing the parameters. So what are the main parameters should be considered? First is the concentration of the reducing agent. Next is the flow rate of the reducing agent, which is the SnCl2. Next is the flow rate of the sample, the flow rate of the purged gas, and the read delay time. So based on the diagram for the instrumental method, so this is the schematic of the VCA accessory coupled with the AAS spectrometer for the optimization parameter of the hydride generation AAS and cold vapor AAS. So basically we can focus on the peristaltic pump, whereby the sample, acid, and the redundant are placed and flowed simultaneously into the peristalsis pump, and whereby the argon gas, which is the flow rate, is placed into the flow container, and the flow container was directed into the gas and liquid separator and the reaction coil. So from that we can obtain the absorption of the spectrum. Okay, next is the procedure. First, the calibration standard for the 10, 30, and the 50 ppb were prepared for the each metal being analyzed in 50 ml of volumetric flask. Next, the mercury was optimized first, since the potassium iodide used in AS, SB, and SC has the negative interference of the mercury. Okay, then the varying concentration of the reducing agent acid solution were prepared in the volumetric flask by weighing the appropriate masses of the reagent and then diluted into 250 ml of the ionized water. To determine the optimized concentration for the reducing agent and the acid, a 30 ppb of standard was used. The AAS was zeroed after each modification and absorbance were measured for each variation in the solution. Next, the deionized water was pumped through the entire system for the 60 seconds to analyze and to prevent cross-contamination. Next, the adjustment knob was tightened or released to modify the flow rate. So to determine the flow rate of each solution, the specific uptake of the tube in the respective solution, which is the reducing agent, acid of the sample, was placed in 25 ml measuring cylinder, and the volume reagent used in 60 seconds was determined to be the flow rate. The pump tubing internal diameter was varied to control the effect of the flow rate. So the internal diameter of the tubing used for the reducing agent and acid was 0.63 millimeter, 0.69 millimeter, and 0.76 millimeter. Alright, the temperature of the air acetylene flame optimized for HGAAS, regulating the flow rate liter per minute of the acetyl gas to oxidant. The acetyl gas and the airflow were adjusted on the gas control interface into the Spectra AA software. Next, the flow rate of the argon used in the VGA77 was adjusted from the flow gauge to the cylinder. Finally, the absorbance of the sample was recorded for each flow rate of the acetyl gas and the argon. Next, the instrumentation was zeroed after each adjustment was made.